Welcome, ladies and gentlemen, to the technical stage of Hydrogen and Fuel Cells Europe at the Hannover Fair 2022. My name is Bernhard Jekyll. I'm the moderator here for today, and we are really proud to present you the newest technology. And we have the principal electrochemist of Ames, Goldsmith, Ceimig, and he will talk about hyper-PEM catalysts optimized through intelligent design. Please welcome with an applause, Doug Stewart.
Thank you. So I'm going to talk today a bit about PEM catalysts and how we approach performance and how structure determines performance in our catalyst. Thank you. So I'll start by introducing the company. Ames Goldsmith is our parent company. They're a chemical manufacturer based primarily in America. We've got sites all over the world. Ames Goldsmith Ceimig is our PGM-based, PGM-focused facility up in sunny Scotland in Dundee. So Ames Goldsmith produces a wide array of metal-based chemicals, mainly silver for a range of applications. At Ceimig, we focus on PGM catalysts for PEM applications, fuel cells, electrolyzers, some sensor work as well. So we've just launched our new range of catalysts under the trade name of Hyper for fuel cells and electrolyzers. And so what I'd like to talk about today is a bit about our design process, how we approach performance optimization. What I'll talk about applies to all of our catalysts, but because we've only got 10 minutes, I'll mainly focus on platinum, on carbon, and how we optimize performance of those particular catalysts. So for us, understanding the relationships between structure and performance is key and forms the basis of everything we do. So when it comes to platinum, generally speaking, platinum nanoparticle size is the main determining factor in activity and durability. But when you examine especially the degradation mechanisms, there's a lot of other factors which come into play, and you can tweak performance. You can vary performance quite a lot by understanding these mechanisms and how the structure impacts these mechanisms. And so up the top there, I've got a range of factors. These are just the ones that I put on the slide. Average nanoparticle size we find is the key determinant, but all of these other factors influence the performance of a catalyst, especially durability. And so we can use our understanding of these factors to tweak performance and durability. So, as I said, average nanoparticle diameter largely influences ECSA. You've got a reverse exponential relationship, which we would expect. And the same with durability. If we compare average nanoparticle size to durability through an accelerated stress test, it's a roughly linear correlation, again, as you'd expect. When we compare the two for individual catalysts, though, there's quite a lot of variation. The correlation is not as strong. And this is an error. This is those factors I talked about and us tweaking different parameters of the structure to get different performance. So I'll have a quick look at these three catalysts in particular. And so what we've got is increasing durability, quite significant increases in durability, with not a huge difference in electrochemical surface area and activity. And so we've managed to achieve this. There we go, through a number of different factors. So the primary mechanism at play here is obviously average nanoparticle size, as I've said. So this is what's driving our increase in durability, but there's no decrease in activity or surface area, which you would expect. And the clue lies in this standard deviation measurement here, increasing standard deviation. So if we look at nanoparticle distribution, and even for a technical forum, I know I'm getting a little technical here. But if you look at the distribution, we're getting movement to a higher nanoparticle size, but also they're widening. And they're widening upwards, which is the key part here. So we're increasing the number of nanoparticles at these very high range, while maximizing the number of nanoparticles in the 3 to 6 nanometer region. And so because activity is a reverse exponential correlation, but durability is linear, increasing the nanoparticles, have I got the laser pointer? No. Increasing nanoparticles in the higher region while maintaining the smaller one gives you a much better durability with very little change to your activity or ECSA. The final factor in this particular catalyst is nanoparticles under 3 nanometers in size are very susceptible to certain types of degradation and durability. And so minimizing the number of particles in this region is key and can result in some significant differences to durability while maintaining ECSA. So this is just a microcosm of our catalyst design, but for these particular catalysts, those changes, and in particular, looking at size distribution and where those nanoparticles sit on the spectrum, gives us a 20% increase in durability with almost no, I think it's a 7% decrease in ECSA. We can, of course, do the reverse. So by looking at these factors and the structure, we can increase the ECSA and the activity of a catalyst while maintaining similar durability metrics. And so to bring it back round, with all our catalysts, we've looked at black carbons, but with all of our catalysts, our platinum alloys, our iridium materials, structure determines activity. And by understanding the structure, we can improve our catalysts. So we work with a number of academic partners and customers to really probe the fundamentals of the materials we work with, how the structure impacts the activity. And it's a circular process, and we continue to improve on our catalysts. And this allows us to produce materials that perform significantly better than some of our competitors. This is one of our high durability catalysts. And then even for the high activity catalysts, we can produce materials that are better across a range of different parameters. So I'll summarize there. Thank you for listening. We are on stand B77. And we're open to conversations about our existing range. We can produce custom grades of catalysts if you want a different loading or a different metal. So yeah, thank you for having me.
Thank you, Dr. Stewart. We've got some time for questions. If there are any questions from the audience right now, you have the chance to ask right now. There's no question. I really liked your accent.
Thank you. I was born with it.
Thanks a lot for this great presentation. And next, for more questions, just visit him at his booth.
Yeah, we're just on the other side of this booth here, just over there. So please stop by.
Okay, great. Thanks a lot.